Okay, here we go. Last topic for 8511, power and alternating current. Now, if you look at the old slides, they have a bunch of stuff about instruments that measure like electrical power or whatever, ammeter, ohmmeter, multimeter. We're going to drop that because we had the extra week off and just cover the last topics from chapter 10. So power, and I know you've done this before and we've kind of been avoiding it. Power is current times voltage. It's also a lot of other things. You'll remember you have that kind of wheel on your formula sheet and you can quickly look up all the various arrangements of that. If it's current times voltage, you can think that it is an amp volt or volt amp. And it's also a joule per second. These relationships mean it has lots of ways of defining the unit, but the unit we're going with is a watt, is the standard one. Okay, so power calculations are relatively simple. And here, when I write down formulas, I'm pretending I have the formula in sheet in front of me. So first one, we're looking for power. We have a current, and we have a voltage. Making sure you're in those base units for these ones. And if you look at your formula sheet, you will see that power is equal to current times voltage. So if I want the power, simply 9 times 110. Very straightforward. You can be given different units. Here we have a resistance of 1.5 ohms and a current. Should call that an I. I'm getting carried away here. 1 second. A current. Here we go. Begun. 2 amps. And if you look at your formula sheet, you see something that says power is also equal to I squared R, or you can derive that from the original formulas that you have. So you're going to take 2 squared, do that first, multiply by 1 by 5, and you should get 6 watts. Okay, now we're looking for R. And we have a power, and we have a voltage. Same thing. R, when I look it up, and they're using E, but I like V. V squared over power, 110 squared over 600, 20.17 ohms. So these are very easy calculations, much like the Ohm's law ones were very easy. Here's a little more thinky-think one. If I have a 1,000 watt oven and a 1,500 watt television in series on the same 110 circuit, will they trip the breaker? Okay, so you're looking for current, right? You want to see whether your current is over 20 amps. So if you have two things in series, the power rule is you can totally add them up. So your total circuit power is going to be 1,000 plus 1,500. So 2,500 watts. And I just want to know if I take 2,500 watts and I divide it by 110, what current will happen? 22.7 amps. So certainly you will blow it. Now let's think about parallel, which seems a little less intuitive. So say we're going to send, and we have our 1,000 watts here, and we have our 1,500 watts here, or in parallel, so that I know that 110 is going down both these, and if I take that 1,000 divided by 110, I'm going to get the current in this branch, right? And if I take that 1,500, that's too many zeros, and I divide it by 110, I'm going to get the current in this branch. And I know for parallel that I1 plus I2 equals I total, like the current will rejoin after this. So the math to get the current in this situation, 1,000 divided by 110 for branch 1 plus 1,500 divided by 110. And guess what? When you do that, you're still going to get 22.7 amps. So the nice thing is about power, you can just kind of add it up, whether you're in series or parallel. Okay, let's go to the store and buy some power. So when you get energy into your house, it's kilowatt hours. Now, energy for this class is not, when you think of energy in physics, like potential kinetic energy. It's kind of a loose term. It's just power over time. So when I say energy, it always kind of messes me up a bit because it's not the way I'm used to thinking about it. But for us, we're just going to say how much energy do you have, and you're really talking about time, power for time. Okay, you're going to have a cost formula. This is key. A little bit of different variable. Make sure your power is in kilowatts. Time should be in hours. Okay, and your unit energy cost, which will be in kilowatt hours, and or dollars per kilowatt hours. And it'll be really, really low because when you see the advertised price per kilowatt hour of energy, it is really cheap, but then you end up running it up anyway. So here's a little example where we had a 550 watt iron, but make sure, this is an epic day of ironing. I would die if I was doing it for 2.5 hours. You're going to take 0.55 and you're going to multiply it by the 2.5 and then your rate. And it's going to be 11 cents to iron that long. And hopefully you got paid. So let's do a few practice ones with this. So we have our formula. I'm going to put our formula up here. Cost equals power time times the rate. Okay, so here I want to know the cost. And I have, now watch it, 0.75 kilowatts, must be in kilowatts. My time is 12 hours, that's fine, and my rate is 0.07. So those are good to go into the formula just like that. $0.07, and it's going to be 63 cents for that lamp. Okay, this time I have my cost. I have my power, I have my time. So I must be solving for the energy cost. And just put it into the formula or rearrange the formula, whatever you're most comfortable with. 3 times 24 times the rate, so 3.84 is equal to 72R, and then of course you're going to take both sides, divide by 72, you're going to end up with the rate equals 0.053. That's in dollars, so 5.3 cents per kilowatt hour. Another one, we're looking for time. I see how long. We have a rate. We have power, 1 kilowatt, watch that conversion. And we do have a cost. It cost us 0.5. It cost us 50 cents. Okay, same thing. Putting them out of order so my numbers are together, times time. And then this is just 0.075, so time is going to be equal to 0.5 divided by 0.075, which is 6.67 hours. 6 hours, 40 minutes if you want to get fancy. Number 4, I don't have a power, but I do have a current and a voltage. So I have the ingredients for power. So my first step here is to find the power by using the formula P equals IV. So I'm going to take 2.5 amps and multiply it by 110. And I'm going to get 275 watts. And remembering before you do these cost formulas, you need to change it to kilowatts. Cool, cool. All right, so we're looking for cost. And we have our power. Our time is 2 days. And our rate is 0.094. Put that second, and you should get $12.41. Okay, so here's the answer for number 4. Here's the answer for number 3. Here's the answer for number 2. And here's the answer for number 1. Not hard, just put things in the right place and use the right units. So alternating current, we are not going to get into the whole physics of alternating current. So when you have direct current, your flow is always the same, your current. Alternating current reverses direction, so it goes back and forth at a very high frequency. Okay, and how do you make it? These are at generating stations. So if you put wind turbines or water turbines going, you're spinning wire, like because a wire in a magnetic field that you're supplying, and just by physics, and that is going to create current. And it's going to flip that wire through the field as it spins, and you're going to change direction a lot. What do you typically get when it comes out? You're going to get a range from 170 to negative 170 volts AC. It's alternating current. So this is the alternating current that you're generating, and it goes like this. Makes a sine wave. Our 120 is right here. So if it peaks out at 170, we use 120 because that's just the effective thing, just kind of accounting for the area above and below the effective value. So do I need you to know this? No. You get 120 volts, you know that. So here it is again. This is DC. You'll see it's consistent, it's happy. But AC goes like this. And often you will add phases just to kind of smooth the curve out and get some more complete things. You might have 3 phase. Just means you have multiple voltage phases. And the more you do that, the smoother it gets. Okay? This is a GIF that is not working, obviously. So the idea is that if you have this thing and the piston is moving this way, you are drawing the water or the current that way. Once you get to the opposite side of the gear, you're going to start pushing, and the piston will go this way, driving the water that way. Okay, why? Why do we use AC? DC seems so much more simple. You know, it's consistent, it's always at the same size. It's mostly because we transmit power over very, very long distances. So if you have a wire going forever, if you're just using DC voltage, your current is quite high. And the higher the current, the resistance of the wire isn't going to change. But if you have high current, that is squared. So you can lose a lot of power, like this would be power lost on the lines over those long distances. The beauty of AC is that you can use transformers and you can create high voltage situations. And if you step up the voltage, your current can go way down. And if your current goes way down, your power loss goes way down. Okay? So these kind of transformers, what they're doing is they're kind of crazy because they're taking, you have a current that is alternating, so it's flip-flopping, and when you have that flip-flopping current, you create a magnetic field. And in turn, if you put another wire nearby or another coil of wire nearby, you can create a second AC current, but it doesn't have to be at the same voltage. It has to be the same power, but the voltage and the current can be varied. So let's look at a very basic transformer. So here is your primary coil. Your primary is your input. Okay, and when I say 5 turns, that means a wire is wrapped around this, usually iron, because it's a good conductor, kind of amplifies, and you're coming in at 110 volts. There's a magnetic field here. Let's draw this, and it's going to induce a current in the secondary coil. Now, you can induce any size of current voltage you want. It all depends on the number of turns that you put in there. So here we've doubled the turns, okay? And you'll notice we've doubled the voltage. And what does that mean about the current? We've probably half the current, okay? So we have this lower current and we're ready to go longer distances with this. If you have the number of turns in your primary is less than the number of turns in your secondary, it's a step up. Because you're stepping up the voltage. If you have the number of turns in your primary is greater than the number of turns in your secondary, it's a step down. And the idea is that when you go from your source to your long distance wires, then you step up the voltage, okay, and step down the current. But don't think of it that way, just think of the step up for the voltage only. And when you get to your house or your little transformer box or whatever you've got on someone's lawn, that's when you're going to take that high voltage and you're going to step it down for residential use. Okay, so the formulas are here. Now, when you do this, you're never going to have a string. You're always going to be solving either, you know, your NP over your NS is equal to your voltage primary over your voltage S. You're going to be setting up a ratio. You won't have a string of all three. And then if you want to solve for current, you'd write another one. The most important thing to notice here is that these are directly proportional. The more turns, the more voltage. But when you look at the current, oops, that's supposed to be an I. Let's see if we can erase this successfully. There we go. Man, not my morning. The secondary is on top because they're inversely proportional. If you ramp up the voltage, you're going to send the current lower. And the other huge thing is you're messing around with voltage and current, but the power in the primary remains the same as the power in the secondary. Let's do some transformer questions. So you'll see here that I've left the formulas up in the corner. And just remember, make a list of variables to keep yourself straight. So here I have a primary coil that has 65 turns. So N for turn, number of turns. My primary is 65. The voltage in my primary is 115 volts. The voltage in my secondary is 2300, and I am solving for NS, number of turns in my secondary. So let's set it up, just looking up here. 65 turns in my primary, don't know how many turns in my secondary. 115 volts in my primary, 2300 volts. So this, in order for this to be true, I'm fully expecting to have X be bigger than 65. I'm going to switch over here. So let's remember that magic banana thing here. So whenever you have two numbers kitty corner, switch back to my rainbow pen, those are the multipliers, the leftover is the divider. So to get X, just going back to straight up math, your math is going to be 65 times 2300 divided by 115. And that's just a cross multiplying shortcut. So you are going to find that when you do that math, you get 1300 turns in the secondary. What type is it? If I go from 65 to 1300, if I go from 115 volts to 2300, that's a step up. Okay, same transformer has a primary current of 9 amps. What is the secondary current? Okay, IP equals 9 amps. So you can use your 115 over 2300 if you want for this. You could use your new one that you found, your 65 over 1300, your NP over NS, and we're going to make the current ratio. Now, careful, look at that formula. The 9, the primary current goes on the bottom. We're going to do everything else the same. Make sure that this is our multiplier, 1300 is our divider, and we get x is going to be equal to, I'm going to put it here, 65 times 9, divided by 1300. And that should give you 0.45 amps. So there you go. You're going to have only 0.45 amps in the secondary, which is perfect. Okay, let's look at number 3. The power in the primary. So we've got the power in the primary is 400 watts. And we have the current in the secondary is 11.4 amps. And I want to know what the voltage in the secondary is. Now, when you first look at this, you might be like, oh, I don't have enough information, but you have to remember that key thing. Power in both the primary and the secondary are the same. So you actually know this as well. Power in the secondary is 400 watts. And this is very simple. Now you've just got P equals IV, right? You don't have to mess with all the ratios. So if you want to solve for the voltage, the power, right, divided by the current, straight up, 35, oh my goodness, I keep hitting the wrong button on my pen, 35.1 volts. Those are transformer questions. And the last random topic that we're going to talk about is generators. So power output depends on voltage and current. Of course it does, because P is equal to current times voltage. We're going to make apparent power. So once again, kind of going back, but not really want to get too into it. If you have your power and your current out of phase, they're doing that, and then you're just going to multiply the effective, that kind of 70% or 80%, whatever it is, value to get it. And when you have apparent power, you measure it in kilovolt amps. Are they the same as kilowatts? Absolutely. IV, amp volt, volt amp. But I think, from my understanding, because this is not the actual power that you're measuring, they keep it in kilovolt amps to just kind of keep you straight so you don't get messed up. Now, the actual power that you get, so apparent power is calculated from these curves. Actual power is measured at the station. Okay, and like everything in this world, you're never 100% efficient. So the actual power is going to be less than the apparent power. And it's just going to be a ratio that we call the power factor. So it's like a percentage of efficiency, but we're just going to leave it as a decimal form. Here's the formula. Power factor equals the actual power over the apparent power. So if you're confused too, first of all, this number is always going to be smaller. And it's also going to be in kilowatts. Whereas this is always going to be the theoretical, the pie in the sky amount, and it will be in kilovolt amps. So if I look at number 1, I have a power factor, so that goes on the left side. And I'm looking for the actual, so I'm missing the top. And I have the apparent power. And the math to get x, cross multiplying, oops, I don't have my paper in front of me, should equal it to be 119.278 kilowatts. Then let's look at number 2. So here we're solving for the power factor. It's our unknown. Actual power 19,500, apparent power 2,650. Actual over apparent. Something that's going to make an answer less than 1, or else you'll be like turbocharged super station. Do that math. It's pretty efficient. And that's it. These are the last topics for this course, so make sure you know these slides and you'll be ready to handle the questions on it on the final.